Hi, everybody. I hope that you were able to get some rest and recuperation time in over the weekend. I do realize it was very hectic. Yeah, I've watched a lot of the news. Um, the show must go on, so we're going to do the best that we can. We are almost through the quarter, and fingers crossed, today's the day. We're almost through chapter 3. Before I do that, though, so I was going to type something up, but I didn't have time to do it because I got into an argument with friends about what it means to be tolerant and why tolerance begets some level of intolerance. And it's a really interesting read if you aren't up on the paradox of tolerance and intolerance and why, in order to be a tolerant society, you need to be intolerant of hate, which is very relevant right now. So, required reading beyond the scope of this class, but that's a different topic for a different time. Um, what was I going to do? I was going to go here, and that's just going to float up in the corner there. I guess I could turn that off, actually. Hold on. PowerPoint. There we go. Okay, so what I want to do... Oh, that requires my Photoshop to actually show up on my screen. Sometimes when I maximize, it doesn't do that. What I want to do first is not select a tiny region, but let's talk about schedule changes, if I could spell schedule. I apologize that you had to read my handwriting for this. So let's see here. So this is week 8, 9, and 10. And so we'll say Tuesday, Wednesday, Thursday. I decided that we all needed an extra day to recover for Tuesday. So you are here on Wednesday, week 8. So we're going to have a lecture here today. There will be no lab lecture this week because there just aren't any more days. There will be another lecture tomorrow, and that will be normal. Then we'll go to week 9, which will be lecture. This will be lab number 5. This will be a lecture. Midterm 2 is Monday on week 10. Tuesday will be a lecture. This will just be a Q&A. And then the last day of class is the final exam. So there is no lecture on the Thursday, week 10. So there are only 5 lectures left. Yeah, midterm, I know. I don't like the word midterm. But I am required to have 2 forms of assessment and the final. And I figure if I just cram them at the end like this, then you do the midterm and then you take the final and it's like, oh, these are all the same questions. I'm like, yeah, it's the same material. If you knew it on the midterm, you know it on the final. No surprises there. And technically that fulfills the requirement. So this is just how I've decided to do it. So you'll notice that there is no Lab 6 on here. Yeah, we're just going to chop Lab 6 off the schedule there. I was thinking about doing that anyway, and now I'm sort of forced to. I can't make you do a lab on Wednesday and then say, oh, turn it in tomorrow. Oh, and there's a final, because that'd be a real asshole thing to do. And with the amount of shit that we're all dealing with right now, beyond the classroom, I think it'll be okay. Anyway, that's the schedule change. So, again, apologize for moving today's lecture, or yesterday's lecture to today. Don't worry about lab number 6. It won't be posted. I haven't even written it anyway. I have written lab 5, though. When are the finals? My calendar says the final exam will be on the 18th. Let me read your question, Jihan. Yeah, so as long as you put the correct label to the correct peak, there shouldn't be a problem. Midterm is, it looks like the 15th, because today's the 3rd, and we're in week 8, and 2 weeks from now would be... Yeah, so that's correct. Whoever was telling me that grades need to be turned in on the 16th, that's pretty much impossible. Unless I am off by a week, and that would be terrible. But also impossible because I've been keeping track of what week this is every... It's right down at the bottom. You can see it right here. If I go like this with the mouse... Oh, you can't actually see the mouse, but... It's right here! Below this cursor! I feel like if I've gotten that wrong, then... Well, fuck me. That's really all I can say. And then we'll have to we'll have to figure out something different. Is midterm going to be like exam 1? Yes. Yes, midterm 2 will be exactly like midterm 1, except it will cover chapters 3.3 onward. Which means that it'll have chapter 3, most of it, and then chapter 4. We might get to chapter 5. Chapter 5 is really short. We kind of just tack it on at the end. Chapter 4 is moderate length. But it's nothing like Chapter 3, which is just this insane, grueling marathon from hell. So let me turn this back on. We'll go back here. And let's put this in, let's put this to bed. So in this section, we are going to talk about molecular and ionic compounds and what they are. So in Chapter 2, we talked about making ions. And yeah, you'll have to do this again because I put it on the quiz a second time without realizing, oh, we did this in Chapter 2. So you're going to need to tell me what ions will be made for elements that are in columns 1 through 8a. And so that would be stuff like this. So if I had, like, say, calcium, and I asked you, how would this ionize? You would say, oh, okay, I want to do this. Or maybe I give you oxygen, and how would it ionize, and you get that. And the reason for this is because ions form when they become a different number of electrons than their protons, but the stable number of electrons tends to be any species that is isoelectronic with a noble gas. There will be a Chapter 3 quiz. It'll be just like the other quizzes. Chapter 3 is 25 points. I actually made it, I think, like 24 questions, and some of them are 1.5, and most of them are 1. So if you're like, man, I really don't understand electron affinity, there's only like 2 questions on it. When will the quiz be? When we finish Chapter 3, I unlock it, and then you'll have a week to do it. So we know how to make these ions. So, for example, if I had selenium here, I know that selenium has 34 electrons. And if I wanted it to become isoelectronic with a noble gas, the nearest one to this is krypton. Krypton has 36 electrons. So if I did this transition, 34 to 36, that would require me to do that. Now, if I wrote out its electron configuration, this would be argon. What row am I in? This is selenium. So 4s2, 3d10, 4p6. Something that comes up a lot when we see noble gas configurations and that they are stable is that whenever we land on the noble gas configuration, we always observe this. The S and P subshell is totally full. And so this is actually going to lead us to something that we're going to use as a shortcut later on. This is the origin of the octet rule, which you've probably already heard of at this point. And you just say, oh, I have to count up to 8 valence electrons. If I can get 8 valence electrons, it's stable. And that's where this comes from. And that's the whole reason we study electron configuration, to see that, like, oh, okay, this is the thing that all of this has in common. We can do the same thing for barium. The nearest noble gas to barium, I hit the wrong button there, that's not what I meant to do, is xenon, it looks like. So here's xenon. It has 54 electrons. And in order to go from 56 to 54, I would have to take barium and remove 2 of its electrons. And since its electron configuration is exactly the same as xenon, I could write that out too. And you would see that it has a full, I'm just counting in my head here, 5s and 5p subshell. Oh, I wrote it on the screen there too, so I don't even have to write that. All right. Now, transition metals, lanthanides, actinides don't really follow these rules. They don't land on full S and P subshells. In fact, they land on kind of their own thing. What we need to remember when we're looking at transition metals, lanthanides, and actinides, etc., is that when we remove electrons, we're always removing valence electrons first. So that means the highest N, and then you just start working backwards. So if I had like something that had the highest N was 5s, and it had 4d electrons, I'd pick off the 5s electrons first, and then I'd start going through N equals 4, starting with D, then P, then S, and so on and so forth. Now, when you do this, you might land on something that has a full S and P subshell. There just might be extra D electrons in there. As a result, this ion is pretty oftentimes stable. And you'll find that there's often a pattern for ions that form in the transition metals and the lanthanides. And that pattern is that you often find that this is the charge that a transition metal takes. For example, let's just grab iron here, for example. So here's iron. Iron is argon 4s2 3d 1, 2, 3, 4, 5, 6. And if I were to take away these electrons, then what would end up happening is I would get argon 3d6, and inside here is our full S and P subshell. So we could say that this ion probably will form. And it turns out it does. Iron 2 is pretty common. And for most transition metals, the +2 ionization state is pretty common. There are some exceptions, and those exceptions occur when you have the D5, D10 rule sort of thing going on. So, like, for example, copper. Copper has an electron configuration that we see does something like this. Because remember, one of the electrons hops over, and then we get rid of that. It becomes copper +1. And so copper +1 is very common. So is silver +1 and gold +1. So these rules tend to follow the exceptions as well. All right, we already did a common ion that occurs for iron. All right, so now what we can do is we have some predictive capacity of figuring out what ions will form for transition metals. And we use quantum mechanics to explain that. We could also use quantum mechanics to explain how iron 3 occurs. Because if you look at something that's D6, and I were to draw the D orbitals, I gotta change my color here so that this contrasts. And I had this electron configuration, it makes sense that iron would say, oh, I'm just going to go boop and get rid of an extra electron so I have no pairs. And so iron 3 is also very common. And so you can make little predictions like that all throughout the periodic table. So using this selection of atoms, what I want you to do is predict the ion that they should form. And then down here for the transition metals, give a good guess as to what ion might form. And then if you could predict multiple ions, try and do that. And we'll show you how to do that in just a second. But for now, start up here with these. These are the ones that I care about and that I'm going to test you on. These are optional, but we'll go over them anyway in a second. So I'll give you 5 minutes to do that, and I'll be right back. I don't know why my cats have decided that now is the time where they want to get into an argument and hiss and yowl in the hallway. So I had to go shoo them away. But how are we doing on these, particularly the first 5? You should be able to predict which ion forms. I'll give you another minute or so to finish, and we'll go over the answers in just a second. All right, let's go over the answers here. I can write directly on the screen. So for fluorine, here's its... Oops, that's not right. That's the target electron configuration that we want. So this is what we have for fluorine. I want it to look like neon, which has 10 electrons. But here I only have 9, so I'm going to add one more, which means that this becomes minus. What do we got for magnesium? Magnesium is 12 electrons, so I'll just do this. I want this to also look like neon. I'll change colors here. Which has 10 electrons, because it's the nearest noble gas to get this full subshell. I can do that by getting rid of these guys, which means that it becomes 2+. And so this is the method behind how we get all of these ions from Chapter 2. So you already knew how to make these ions, probably from 140, but this is where it comes from. We use the electron configuration to determine the ion that forms so that we have a full S and P subshell. Now, doing this similarly for these 3, these are the charges that you should get. So when you write out the electron configuration for, say, cesium, you're going to have a whole bunch of S and P and D stuff. But at the very end, in the valence shell, there should be a full S and P subshell. All right, down here, for our elements, what you're going to do is predict common ions for them based on their electron configuration. I'm going to pick vanadium because it's probably the most interesting of these. So vanadium has the electron configuration argon 4s2 3d. I think it's 3, right? And if I take my vanadium and I get rid of this, then it will have a full S and P subshell in here. So vanadium 2+ should be allowed, and it is. Now, if I had to predict another ion that would be stable, remember that this is what I want. I want my full S&P subshell. And I've already got that in the argon core. So what I could do is I could do this. Or I could do this. Or I could do this. Oops, that's not what I meant to do. I wrote. I'll just get rid of it entirely. Here we go. And that would make that. And so we would actually expect vanadium to be any of these possibilities. And it turns out that vanadium can do all of these things. And this is actually very rare. Most of the time, the ones that are stable are going to be the ones on the outside. So 2 is stable, and then 5 would be stable. For manganese, this is true. Manganese is very stable with +2. It's very stable as +7 because it has a bunch of electrons it can ditch. And then right in the middle is manganese 4, which is actually stable. But vanadium is actually really cool. And let me see if I can get this really quickly. When I was in graduate school, I took a class from an inorganic chemist, and he showed us this vanadium vanadial ion. I don't know if this video is what I want. Let me hit mute because I don't want to. How about this one? Yeah, this will work. So if I go here, vanadium is just really cool to look at. There we go. So this is vanadium. And I believe this is vanadium. I don't know if this is vanadium 5 or vanadium 2. But what happens is that we can add stuff to it, and you can get a different oxidation state. So yellow must be 5. So if it's vanadium +5, it's yellow. But if it's +4, it's this color. And if it's +3, it's this color instead. We gotta shake it up. And you can see that that's actually very, very different. And then if it's +2, and you let it sit long enough to do that, then you get purple. Purpley blue. There you go. And so you can actually get all different colors of ions for vanadium. And as somebody who did this as their career, I went into inorganic chemistry purely for this reason, because in organic chemistry, all of your compounds are white. If you make a mistake, they're brown because they oxidize, and oxidation products tend to be brown. And so you can never really tell if you did it correctly. But in inorganic chemistry, hey, is my compound supposed to be purpley blue? Yeah, you did it right. Hooray! You instantly know. So I was like, ooh, I want something that has all these pretty colors. That's literally the reason I went into inorganic. I found all of the chemistry fields super interesting, so I was like, I just want to pick the one that's the prettiest. So you know. There you go. Alright. I'm going to skip over the rest of these because you can do something similar. I just want to show off vanadium because it's fun. Alright, so when we are making ions out of these elements that we've been talking about, what we form are called monatomic ions. Monatomic ions are just individual single atoms with a charge on them. Now, polyatomic ions do exist, and they are a bunch of atoms that are all bonded together, but between those atoms, there is a difference in the number of electrons compared to the number of protons of all the atoms that are in there. And that could just be because more electrons were added to make bonds or whatever. The end result is that the overall molecule, we'll call it, ends up having a charge, and then it becomes a polyatomic ion. So an example of this would be azide. So for instance, if I look at N3-, and I was counting the number of electrons in here, each nitrogen individually has 7. And there are 3 of them. So there should be 21 total electrons in this thing. But then I have this charge right here, which means that I have an extra electron. Now, this is the total number of electrons. Later on, we're only going to care about valence electrons, so this example is going to seem kind of silly. I might have just answered your question. I'm speaking to you from the future. But it's 7 total electrons, because nitrogen is element number 7. Yeah. If we were counting valence electrons, it would only have 5. And then we would have 5 times 3 plus an additional 1. So, and that's why I'm mentioning that down here, because in chapter 4, we don't care about total electrons. We care about valence electrons. But that being said, to count all of the electrons, we do have to count... Oops. We do have to count this minus sign. That's not what I meant to do. There we go. We do have to count this minus sign when we are counting electrons, whether we're counting valence or total. Now, we're going to use that ability to count electrons in compounds and ions to figure out how bonding works. And so, first thing that we want to do, before we get to chapter 4 and we start talking about bonding and drawing structures, is figure out what bonds actually are. And that's exactly right. Electrons that are valence are the ones that are involved in bonding. They're the only ones we care about. So let's talk about how we get to creating an ionic bond. So far, I've told you that, hey, you just put a plus and a minus next to each other. But how do you exactly do that? Well, first of all, you got to find some species that have these charges. So that could be like a polyatomic ion, either a metal that is an ion or ammonium. And then you need some anion, which could be any monatomic anion that we've seen so far, or any polyatomic ion in the list of ions in the beginning of chapter 3. Now, in order for an ionic bond to form, we have to have a cation. And so what that means is that you have to have a metal, or you have to have ammonium. There are other cations that exist, but for our class, these are the ones that we care about. So if you are looking at a compound and it has one of those things in it, it is an ionic compound. If you see like CO2, there are no metals in that. There is no ammonium in that, so that must not be an ionic compound. And this is going to be your test. You're going to be trying to figure out what types of compounds are and then give them a name in chapter 4. And the way that you determine their name is by figuring out whether they're ionic or covalent. And this is a very important first step. Now, let's suppose that these charges that I can't seem to highlight because yellow doesn't show that. Let's suppose these charges didn't exist. How would you take elements that have no charge and then form an ionic compound out of them? And the answer to that is, well, we can move electrons around by causing a reaction to occur, and then we'll form the covalent bond. We are concerned about other polyatomic ions, but NH4 is the only positive one. All the rest of them are negative. With the exception of hydronium, but hydronium doesn't actually make ionic compounds. I mean, I should say, as we understand. Yeah, it's the only positive one. Or it should be the only positive one in your list. Everything else is negative. That said, there are more polyatomic ions than the ones that are listed on the table, but that table is enough. Yeah, there's plenty. So, going back to our question here, if I want to make this out of these two ions, that's easy. But what would happen if I just had these elements? What would happen if I put them together? And so they should react to make an ionic compound, but how exactly does that come about? And this might be the crappy video. Is this Lonnie's lab? No, it's actually the good video. Okay. Alright. So, this is Lonnie. Ah! He's creepy. So I'm going to hit play. And Lonnie's going to do a demonstration on how to create an ionic compound out of sodium metal and chlorine gas. Now, this is before the quarantine, so Lonnie doesn't have any safety equipment on. Before I continue, I do want to show you inside this chamber here, you can see a kind of yellowish gas. You can kind of see how his lab coat is a bit, like, discolored by looking through this. This is chlorine gas. Chlorine gas is sent through this cylinder into this chamber, and any that tries to escape then gets pulled down this vent. So Lonnie's actually really safe here. He's a professional who works at UC Berkeley, it looks like. This grating is just a ventilation system that pulls any fumes or air down into it. So it's not a fan, it's like a vacuum. So anything that's in this region is relatively safe because you're just breathing the air around it. I used to work on these things all the time, and the suction that they have is ridiculous. If you put a piece of paper on this, it would actually get pulled into those little tiny grates, and you have to not put paper on the vent. Anyway, back to the experiment. What Lonnie's doing now, he's taking a piece of sodium. Sodium is stored under oil because it would react with the moisture in the air. He put it in hexane. This is hexane to rinse off the oil. Hexane itself evaporates very quickly and is also very flammable. So when he puts this in the little ladle here, and then puts it in the flame to heat it up and burn off the hexane, and also give the sodium a little bit of energy, you'll see that the bright orange light right there, that's indicative of just like some sort of hydrocarbon, like when you light paper on fire. But then later on, the sodium starts to glow very, very bright orange yellow, which you might have seen if you took Chem 140. And then finally, you just introduce the two together. Here's really hot sodium and chlorine gas, and this is what happens. You can see some of the gases coming out and going straight down the vent. What's being formed here is gaseous sodium chloride. So this is table salt if it were a gas, which you might think, huh? Table salt is not a gas, and yeah, you're right. You have to heat it to 1,000 degrees to do that. And so it's really, really damn hot in there. In fact, what I want you to see is when the reaction is done and he pulls out the ladle, look at how hot the ladle is, even a few seconds after the reaction is done. We'll even pause it for you to see. There we go. So I'm going to just frame forward one at a time. And you can see that that ladle, it looks like there's a red gumball at the end of the stick now. And that thing is just red hot. Because that reaction releases a lot of energy. So much energy that the ions inside are still bouncing around. But you can see that at the bottom, and sort of along the sides, it's starting to make table salt. And this is a sample that Lonnie actually prepared earlier. So by taking sodium and chlorine gas, we've turned two things that are toxic and deadly into something that is delicious. No, Lonnie, what are you doing? You're in the laboratory. You're not supposed to have food in the lab. You're not supposed to eat your experiment, Lonnie. Oh, goodness. I mean, that's old white men for you, right? Alright, so that's how we make ionic compounds in the laboratory, right? Now that we've seen how that happens practically, let's talk about how that occurs at the atomic level so we can understand the why here. So we made these ions. If I were to write out the electron configurations... Yeah, god dang it, Lonnie. This is literally why we can't have nice things. That's Lonnie's lab. He's allowed to live his best life, I guess. I don't know. So what we did here is we did what's called an electron transfer. And what I did was accidentally mark on the screen. So I have this extra electron right here, and I have a space where I can move it to in order to get a full S&P subshell for both elements. And so I can underline that in red right here. So by removing this electron, this would be my full S&P subshell. And if I put this electron here, now I have another full S&P subshell. So for any combination of atoms that you pair together, you will find some way to move electrons around such that everything results in a filled S&P subshell, which later on we're going to call an octet. There will always be some way to do this. You just might need multiple atoms. For example, if I had magnesium instead, which is this, I didn't mean to write it that big. What I could do is I got to get rid of both of these electrons so that here's my full S&P. I could give one electron to each chlorine to make each of them Cl-, and then this would be 2+. So I can electron transfer however I want to get rid of all my electrons off of my metal and give those electrons to the nonmetals because they want the electrons to fill their S&P subshells, and the metals want to get rid of them anyway. So for the examples that I'm showing here, these aren't involving transition metals, so I'm getting rid of S electrons. But the end result is that we want to do this. So wherever our electrons come from, we want to have S and P subshells full. And this electron came from the S orbital, but I could have just as easily gotten it from a D orbital on, say, iron. The origin of the electron doesn't matter because all of the electrons are just electrons. They're all equivalent. But the end result is that we want to have S and P subshells full on the highest valence level, and that will be stable. And that's sort of the whole goal of the discussion is, how do I make a full S and P subshell? I got to erase this so that you can read what I wrote there. But the formation of the ionic bond forms as a result of this. So in doing this, here's my full S&P. Here's my full S&P. Now that I have two stable ions, they won't react further, and then now they see each other and form the ionic bond. Correct, though when you say full outer shell, you just mean S and P. We don't really care about D very much, or F, for this discussion. The D and the F electrons just kind of hang out. They do interesting chemistry, but it is beyond the scope of this class. That's more of a 300 level question about what D electrons do. I would love to talk about D electrons because they're really awesome. But I do want to finish chapter 3 today. So, all right. So, when we make an ionic compound and we start moving electrons around to get full sp subshells, we're going to get some sort of charge, and we're going to make ions out of that. So, I don't know. I'm just going to write down some examples here. So, this. Let's do this. There we go. Any pair of these ions, and all the other ones that you can make, so I just picked a bunch. You could pair any of these together as long as they're positive and negative. But they will continue to pair together until the total charge of all of the ions is 0. So if I paired together magnesium and sulfur, the total charge would be 0, and this is a compound that could form. But if I paired together magnesium and nitride, then the total charge here would not be 0. And so this would continue to accumulate ions. In other words, this thing that's left over, its total charge is -1, it would attract something positive. So I would end up with something like this. Oops, that's not the total I wanted. Now it would attract something negative. And now it would attract something positive until its total charge is 0. Because each time I attract an ion, the charge changes. And until things stop having a charge left over, then it's going to just keep attracting the opposite charge and the formula will keep changing. Now, of course, I'm simplifying this. This is not actually how ionic compounds form, but it's a good mnemonic to think, oh, okay, I could just put things together by adding them one at a time and count the charge that way. The other thing that you can do is you could say, okay, I'm going to pick this guy and this guy. How do I put these two together and get a total charge of 0? Well, right now my total charges are positive 3 and negative 2. I need more negative, and I got to make it a multiple of this. That seemed like it would work better in my head than it did here. So I could do this. I can erase everything. Goodness. So you do it like that. So you're sort of balancing equations, but this is not really an equation. You're balancing charge here. So the formula that would form out of these two ions would be there's 2 aluminums as ions, and then there's 3 sulfides as ions, and then there is no net charge in this spot that my little buzzy electron is zooming around. I accidentally marked with my pen. I need to get rid of that. So this would be the ionic compound that you form. So you can form ionic compounds by putting together any 2 pairs of ions. The same is true for polyatomic ions. It's just that the charges on polyatomic ions are fixed. So if I asked you to predict the formula that would occur between magnesium and iodine, first you got to figure out what ion forms from using electron configurations and making a full S and P subshell. And that's this one. Now you got to do the same thing for iodine. And then you have to put enough of these together to create the formula. So what is the formula for this compound? It's just this, MgI2. Because I need 2 iodines to form 2 iodides to make my ionic compound. So I believe on the next slide I have a bunch of things. Oh, we just have polyatomic ions. So polyatomic ions do the same thing. For example, if I took ammonium and sulfur to make sulfide, to get ammonium sulfide, the formula that I would get for that would just be to put 2 of these ammoniums together until the charge cancels out with the sulfide. And there you go. There are the ones that I want you to do. So what I want you to do here... Oops, I didn't mean to click ahead there. What I want you to do here is I want you to try and figure out the formula of each of these pairs of elements, and then you got to go down to your list of polyatomic ions, which should be at the very beginning of Chapter 3, and figure out the formula for these compounds too. And we'll go over the answers in about 5 minutes. First, write out the ion that forms. For example, on this first one, sodium's ion would be sodium plus. Nitrogen's ion would be N3-, and then put them together to make an ionic compound, okay, by balancing all the charges. All right, I'll see you in a bit. All right. Hopefully everybody is almost ready. I just need to... Okay, never mind. Yeah, that's fine. So let's go over the answers here. So I'm going to skip writing out all the electron configurations because I'm going to assume that we know how to do that now. And that we know which ion to form, particularly because this was covered in 140. For cesium, the ion that you would make is plus. For bromine, it is Br minus to get bromide. And so that would give us cesium bromide. Then we have magnesium, which was 2 plus. We have oxide, which is O2 minus. Makes MgO. Got aluminum, which is 3 plus. Phosphorus is 3 minus. Putting those together makes aluminum phosphide. And then finally, aluminum is still 3 plus. Selenium is 2 minus. We have to be a little bit creative on how we get there, but we get to Al2SE3. And again, this should all be review. Down here, I'm just going to write down the formulas because we're going to run out of time before the break, and I want to finish chapter 3 before then. So there's ammonium and oxygen, because ammonium is NH4+, plus, and oxygen is O2 minus. Oh, I just said I was going to write down the answers here, so there's that one. I gotta switch back and forth between colors so that you don't get confused here. So chlorate is ClO3 with a -1 charge. Aluminum is +1 or +3, so I should do that. Actually, let me write out these ions because just in case you haven't found them in your list. So this is barium. And then cyanide is that. And so knowing how to make the ionic compounds out of polyatomic ions is really just a matter of, do you know what the polyatomic ions are? So if you knew that phosphate was PO4 3-, you treat it like anything else that has a 3-. For the chlorate, no, because each chlorate is -1. Aluminum is +3. And so you need 3 -1 charged ions to cancel out the +3 of aluminum. I can show that on this. Oops, that's still up there. We don't need this anymore. So this is chlorate. And I need 3 of them. So that's my formula. And yeah, there's a bunch of different polyatomic ions in there, so just be careful that you're not picking and choosing the wrong one. A lot of the names are going to be very similar, so just be mindful of that when you are doing the assessment. So when you take the quiz, make sure you, if I ask you for perchlorate, make sure you don't pick perchlorite or something like that, or hypochlorite, or whatever the differences are. All right, last little bit of this chapter. Hooray! Just some rough properties about ionic and covalent compounds. I'll show the demo. Fine, I'll show the demo. I forgot that I had this here. It only takes a minute. I guess we'll watch it. Is this the right web browser? Yes. Otherwise, it'll just open my email. So, ionic compounds conduct electricity. This is not an ionic compound. This is just showing that the circuit turns the light bulb on when it's complete. It is connected to a battery. But if you put table salt, which is an ionic compound, in, we'll find that the ionic compound conducts electricity. Nothing happens. Why didn't it happen? Well, it didn't happen because solids don't have mobile ions. But an ionic compound has ions in it, and if you can make those ions mobile, then you can move charge, and that's how electricity conducts. So if we melt this and make it a liquid, the ions can then move, and the light bulb should turn on. And there it goes. So ionic compounds conduct electricity when they are either solutions or if they're molten. Now, as this cools, it will solidify, and then the ions become locked in place, and the electricity can no longer be conducted through the ionic compound. And you'll see the light bulb slowly goes... There it goes. That was my video. Alright. Now, other properties of ionic compounds is that they tend to make these like square, crystalline sorts of shapes. And this is just because when you have your lattice, they tend to build in positions adjacent to neighbors and not, say, on the top. Because there's just more neighbors that are charged than they are attracted to those positions. Because all of the ions have charge that propagates in all directions, for example, this chloride right here, is attracted to this neighbor and this neighbor and this neighbor and the one behind it and the one in front of it and the one on its side that aren't shown. That charge goes in all directions, so these things are extremely stable. They hold onto each other really well, and you have to heat the heck out of them in order for them to melt. This is why that acetylene torch was needed in order to melt it on the previous slide. You can't do that with a normal, like, stovetop. Whereas with molecular compounds that are not what we've been discussing, molecular compounds are much easier to split apart. I'm not sure why there's a line on my viewer here. What is this? Hold on. It's like this line. I don't know what this is. I'll figure it out later. Okay. As long as it's not showing up on your screen. Molecular compounds, on the other hand, are quite different from ionic compounds. They don't have high melting points. They don't conduct electricity. There must be something totally different about them, which is the whole point of Chapter 5, and what we're going to talk about then. So, the best way that we want to use to figure out whether a compound is covalent or ionic is to figure out its physical properties, such as looking at its melting point, looking at is it conductive, etc. Or by looking at the formula and using the formula to determine whether it has metals in it or ammonium. And if it has any of those, it's not molecular. It must be ionic. Alright, so here are just some physical properties of molecular compounds. Like we said, low melting points, often liquids or gases at room temperature. They don't conduct electricity. Common things are water, oxygen, CO2, sugar. You're going to see a lot of covalent compounds in Chapter 5, so we're going to mostly save that for then. Chapter 4, we're going to spend more time on ionic compounds themselves. So, really quickly, let's just do this because this is the last slide. Hooray! Let's look for things that would tell us if it's ionic. And so what you want to do is you want to look for metals again. Do I see metals? There they are. So either metals, metal cations, or ammonium. Keeping in mind that ammonium won't have this shown in it, but if you see NH4 in the compound, it must be ionic. All right. Any questions on molecular versus ionic? Or Chapter 3, because that is it. Holy crap, we did a lot in Chapter 3. That's why it takes 3.5 weeks to do. But what did we cover in Chapter 3, and what will you be quizzed on the Chapter 3 quiz, which should be like an entire exam on its own? You're going to be tested on light. Make sure that you understand how light behaves, what the formulas are relevant to light, how light behaves as a wave, and how it behaves as a particle, and know what the different parts of the electromagnetic spectrum are, so like infrared versus those are the same thing. Infrared versus UV versus X-ray versus gamma ray versus visible, etc. The Bohr model, make sure that you understand how the Bohr model works, how the principal quantum number and how electrons bouncing up and down give you wavelengths of light using the Rydberg equation. Yeah, it feels like forever ago. That's because it was. Make sure that you understand how quantum numbers work and SPDF orbitals. These are really, for this section right here, these are really the main points. Again, I'm not going to test you on the de Broglie wavelength. We talked about de Broglie wavelength, but it wasn't super relevant to us in this class, and that's okay. Make sure you can write the electron configuration of any atom, any element, any ion. Know the common exceptions, such as the D4 and D9 rules. Tell me how you fill orbitals using the Pauli exclusion principle and the Aufbau principle and Hund's rule. Make sure you can draw a diagram, or at least recognize a diagram for putting in electrons. Distinguish between valence electrons and core electrons. Make sure you know all of our quantum mechanical trends and be able to describe them using quantum mechanics. So know what atomic size variations are. Know how ionization energy is affected by position on the periodic table. How electron affinity works. And then tell me what Z effective is, how you use it to understand these. Tell me different things about the periodic table, such as the horizontal and vertical coordinates, what those are called, groups and periods. And then tell me what different columns are called. And finally, everything we did today, tell me if something is molecular or ionic. That's the end of Chapter 3. Hooray! Finally, peace and happiness return to Chemistry 161. This ends Chapter 3. Oops, that's the wrong thing. There we go. I'll see you after the break.
every world.
Oh, I tried to cheat. Oops, let me turn this down. I ended up resetting the timer. I was like, oh, I'll just start it again and hit it really quickly. No, that's not going to work. Let's get rid of these. Hey, did you guys know... Oops, I didn't actually hit the button. There you go. Hey, did you guys know that there are chapters other than Chapter 4? I didn't. This is news to me. Sorry, I'm just tinkering with something here to get rid of this stupid line that's in my way. There we go. All right, Chapter 4 is the other big chapter in the class, which is not something I should be saying midway through Week 8. But this is pretty much it. Once we're done with Chapter 4, we're done. And there is a little bit of Chapter 10 in here. And the reason for this is actually so that we can line our class up a little bit better with biology. If you're going into cell bio, because you're a bio major, you'd need to understand the intermolecular forces before you start taking cell bio. Otherwise, the whole reason that cells stay together doesn't make any sense. So we throw this section in here early so that you can see it, because you use Chapter 4 stuff to explain it. In fact, you're going to use what we talk about today to explain it. And then when we get to polarity and geometry, we'll tie it all together with a nice, neat bow. So the first thing we're going to talk about is what is the difference between ionic and covalent bonding at the molecular level in terms of electrons. And if sharing electrons is covalent and transferring electrons is ionic, what happens if you end up in between that? Or is there a gradient, basically? Turns out there is. Then we're going to name stuff and draw stuff. That's the whole point of Chapter 4. So we need to be a little more specific about what bonds are, because we can't just magically stick atoms together and say, it's bonds, woo, and wave our hands. That's not really descriptive. That's not going to help us. So we need to describe bonding at the electronic level. And the premise of Chapter 4 is going to be that we're going to do that at a very high level of detail. So a chemical bond is any interaction that holds two atoms together in a molecule. Now, depending on the nature of that bond, we're going to categorize it as either ionic or covalent. Or there might be somewhere in between those extremes, and we'll call it polar covalent. Now, all bonding occurs by manipulating electrons. So whenever you move electrons around, the result is bonding. If I make a bond between two new atoms, I have to put electrons between those atoms. If I want to break a bond, I move the electrons away. If I want to rearrange bonds, I move electrons from one place to another. Everything involves electrons, and specifically, the electrons that we care about are a certain set of electrons that you might remember. Valence electrons. These are the ones that participate in bonding. And so the whole point of Chapter 3, when we were doing all of that discussion about electron configurations and stuff and figuring out which electrons were the valence electrons, was to discover that only the valence electrons bond. And now we're going to give you a shortcut, and you're going to be like, wow, we just spent 3 weeks learning something we're going to throw out the window. Not quite. The foundation for Chapter 3 in quantum mechanics is very important, and we are going to use orbital shapes in Chapter 5. But from this point forward, we are just going to kind of put what we learned in Chapter 3 on the back burner and say, okay, we know it, we understand it, let's move on. So by manipulating these electrons, we're going to create bonds. And the electrons we're going to use are valence bonds. Or valence electrons, sorry. We've already talked about ionic bonds in the general nature. And we've also talked about it in the previous chapter, how to make neutral elements into ions so that you can form ionic bonds. So this slide is not super useful to us. But on this slide, what I want to show is how the lattice for our ionic compound is formed. And I sort of briefly mentioned it at the end of the previous section. But if I was an atom in this position, my charge will extend to all directions. And when I said atom, I actually meant ion. I apologize. this chloride has a negative charge that propagates outward. And so what it's going to do is it's going to try and surround itself with sodiums. And these sodium ions are going to do the same thing. They're going to surround themselves with chlorides. And so on and so forth until this propagates forever. Because, and this would be for an ion that's in the center here, I would have 6 neighbors and all of them are attracted to me. Because those interactions are so strong, this number that's generated, showing the energy required to break those bonds, is extremely high. Now, you might remember the unit of joules from when we were talking about light, how joules are the amount of energy something has. So like a photon of light has a little tiny amount of energy in it. Or like light of a certain wavelength has a certain amount of energy, or so on and so forth. This is so much energy that it requires a lot of heat to do. You know, I thought when I thought about commenting on that line and just saying like, hey, it's Seattle, but it's the quarantine, and I don't want to tangent any more than I already have. Yeah. That quote's going to end up on Reddit. That's great. That's fine. Now, in the region that I've circled here, let me erase my cursor there, or the little arrows I drew. In this region that I have drawn right here, and that highlight isn't super effective, but that's okay. You'll see that there is a small representation of the formula of the compound right there, NaCl. So here's my Cl, and here's my Na. And if I were to take this guy, and I hit copy, and then I just paste, I could make the entire structure out of this. And so what this simplest structure is called a formula unit. The formula unit is the particle of an ionic compound that you can copy and paste over and over and over and over. Now in 162 you're going to learn that I'm cheating here. I just circled 2 atoms and I'm copying and pasting that. In reality, you should be doing this in a cubic sort of pattern that you could repaste, like a stamp or something like that. And you'll learn about how a unit cell is constructed, but that's not in Chapter 4. We haven't done any thermodynamics, and we haven't done any, like, bond energy calculations yet. So that wouldn't really help us to study solids in that level of detail. But just keep in mind that, like, what I'm showing you here is a major simplification, just to let you know what a formula unit is. For molecular compounds that have covalent bonds, there's no charges, so they do not form these lattices. Instead, what they do is they form individual molecules that are just sort of floating around on their own. Those molecules interact with each other through intermolecular forces, which we'll talk about at the very end of the chapter. But for the most part, covalent molecules are just independent entities that are on their own. And the rubric that we're going to be using is, hey, are there only nonmetals in this substance? And if the answer is yes, then the molecule that we're looking at is covalent. And for this class, 99% of the time, that's good enough. There is the ammonium thing that you have to watch out for. And then there are other examples where you can get some metals in there that actually do form covalent compounds. And we're going to see that these are just extremes that we are defining, ionic and covalent, and that there's this whole spectrum in between. Now in Chapter 5, I'm going to show you this picture again. But in order to make a covalent bond, what we actually do is we take 2 atoms, and we take their orbitals, and we squish them together. And what you try and do is you create a region in the middle where your orbitals overlap. And then you put the electrons in that overlap so that they belong to both atoms. The more overlap you get, the stronger the bond. And so you'll see that as I put 2 atoms together, here's the energy of attraction. Here it's 0. Now my my two atoms are attracted to each other greatly because the sign on this is negative. Remember Coulomb's law. As I push things together and the radiance decreases, this number should go up. And if these are opposite charges, which the nuclei and the electrons themselves are, I will get a negative number and there should be an attraction. But you'll notice that something happens here, which is curious. This should just keep going like this as my entities get completely overlapped. But in reality, it ends up doing this thing. And the reason for that is because in the center of these are nuclei, and if the nuclei get too close to each other, they repel. So two atoms will overlap to some optimum distance. And we'll talk about this picture later on in more detail. But the optimum distance that forms is what's known as the bond length. So in covalent bonds, we will always form some idealized bond length, which happens to be the average between maximized overlap and minimized repulsion from the two nuclei. And so this diagram shows you the kind of energy well that the molecule would settle into. And that if you wanted to break this bond apart, you would have to provide at least this much energy. Kind of like as if it were an electron diagram. Now, the picture that I have down here isn't the best to see, but each of these water molecules is independent. How is the bond length determined? Experimentally. So what we have to do is we basically have to use an X-ray diffraction or electron diffraction microscope and collect data based on where electrons diffract to. And then we calculate the bond length that way. So we can't observe it. We can't take out a ruler and be like, how far apart are my hydrogens? We basically bombard it with X-rays and then do a calculation. In this picture that I have here, these molecules are independent and separate. We're going to talk about how independent individual molecules create attractions. And that those attractions are not bonds. So, if I were to draw this bigger, here's water. I'm drawing its Lewis structure. You'll see this again later. And I could draw another water molecule, say, down here. And so this right here, these are bonds right there. But this attraction here is an intermolecular force. And so intermolecular forces are not bonds. So we will talk about intermolecular forces specifically in their own section and how they allow stuff like water to be a solid at any temperature at all. Now, the main premise behind these two extremes of behavior is governed by this property called electronegativity. In a molecule, or in an atom anyway, electrons are always attracted to the nucleus. Some nuclei, however, pull electrons towards them more than others. And there is a quantum mechanical way to explain this, and you should actually know it. So, let's first talk about what the observation of this property is, and then we're going to try and find a quantum mechanical way to describe it. So, if electrons can be transferred from one atom to another to make ionic bonds, or you could just share electrons between two atoms, is there a midpoint where you can sort of do both? Can you have electrons shared unequally? And it turns out that the answer to that is yes, you can. You can think of this sort of thing as maybe you have children and the children share their toys, but one person is apparently going to grow up to be a loan shark, and maybe she gets the toys for 70% of the time, and then her brother only gets them for 30% of the time. because she has the toys just closer to her. Maybe they're in her room or something. I don't know. So atoms are like this too. Atoms can share electrons unevenly. If different atoms form covalent bonds with each other, they will attract electrons to their nuclei more strongly or less strongly than their partner. And let's look at an example of this like this. So right here I have a bond for Cl2. Each of these atoms is chlorine. Chlorine has a specific atomic size, it has a specific ionization energy, it has a specific electron affinity. And what that means is that chlorine is going to want to pull the electrons in the bond towards its nucleus. Now, depending on which side wins, the electrons will get closer to one side or the other. But they are exactly the same strength because they're both chlorine. They're identical in every way. In this case, the electrons in this bond will spend roughly 50% of the time closer to either side or the other because they're the same atom. And so what we say is that the electron density in this bond is very, very equal. So if I was to draw electron density like this, my yellow line represents where the electrons would be, and they would be equally distributed across the entire thing. Now, what would unequal distribution be? Well, if I had a different atom that did not pull electrons as closely to itself, such as, say, this one, now the electrons will tend to move towards one side over the other. Now, knowing what you know about hydrogen, you could look at hydrogen and say, well, it's only got one proton, so it's not going to pull electrons to itself very well. We haven't seen it really used as a cation or an anion. We do know that hydrogen is abundant, and it's tiny. And tiny things tend to have higher charges, but if there's only one proton in the middle versus chlorine's ridiculous number of protons, then what's going to end up happening is that the electron density is going to be more on one side than the other. That was really the best I could draw with the highlighter there. Chlorine pulls the electrons closer to it because its electron affinity is very high. Hydrogen's electron affinity, not very high. And so as electron density moves towards chlorine, it has the electrons closer to it more of the time. And what this results in is a specific property called polarity that we'll talk about at the end of Chapter 4. Well, keep in mind, electron repulsion only occurs between electrons that are in the same orbital, or at least relatively close to each other. In chlorine, these electrons are in 3s and 3p. This electron would be in 1s. 1s is really, really tiny, so if I shove all the electrons over towards hydrogen, then the electrons are really close, and they're actually putting more... they're actually undergoing more repulsion with their close proximity than the ones in chlorine are. But it's good to think about this in terms of electron-electron repulsion. That being said, something having more electrons does not mean it has more electron-electron repulsion to push everything else away. There will be more electrons repelling each other just by virtue of there being more electrons, yes, but the overall effect of electron-electron repulsion can be reduced. And that's just because larger atoms are bigger. There's more space to put the electrons in. In 162, you'll actually learn that some of the ions that we're telling you, like oxygen with O2 minus, turns out O2 minus is really unstable unless you put in an ionic compound. And the reason for that is just trying to push electrons into that tiny space is really hard to do. So there are a lot of weird things going on with this behind the scenes, but I'm trying to simplify it. But it is good to be thinking like, oh, could this be a thing? And then really the only way to determine if that's the answer is to do the experiment. And by do the experiment, I mean we bombard it with X-rays like we do everything. Now, what properties will determine how my electron density moves in one direction or the other? Here are the principal things that we're going to use. Most importantly, we're going to consider Z effective, because Z effective is really everything we care about quantum mechanics is Z effective. If Z effective is higher, something's going to pull electrons towards itself more strongly. Electron affinity is really a function of Z effective. Things that have higher Z effective have higher negative electron affinity. So in this case, I could say, well, hydrogen's Z effective is just 1+, and chlorine's is 7+. So the electrons are probably going to move in this direction towards chlorine. There's just more of an attraction. Now, comparing Z effective is very difficult when you have different n sizes, because if I look at n here, you might say, well, this one's smaller. How is that affected? And it's hard to say. So we made up a whole entire property to streamline this process, and it's right here. It's called electronegativity. This is Linus Pauling. Linus Pauling came up with electronegativity as a concept, and what he did was he did a bunch of calculations to consider Z effective, electron affinity, ionization energy, electron orbitals, orbital overlap, and all sorts of things, and two results occurred. One was he came up with this scale called electronegativity, which ranks atoms based on their ability to pull electrons towards themselves. Higher electronegativity means that all of the quantum mechanic effects are combined and rolled together to produce an atom that is more strongly attracting than its neighbors. That was the first thing Linus Pauling did. The second thing Linus Pauling did was he went insane. He literally lost his marbles and started just touting the effects of, like, vitamin C or something like that. He went absolutely nuts in his later years, which is a shame, because electronegativity is a really good thing, and Linus Pauling deserves to be credited for that. He just completely dove off the deep end into pseudoscience at the end of his profession. So let's talk about electronegativity. Electronegativity is a scale from 0 to 4. 4 is the most electronegative, 0 is the least. Something with an electronegativity of 4 is the strongest entity and will always pull electrons towards itself more strongly than anything it is partnered with. We will always be comparing two atoms when we look at their electronegativity. Now, really important, be careful that you don't confuse electronegativity with electron affinity. They're related, but they're different. Strictly speaking, the electron affinity is used to calculate the electronegativity. Electron affinity are energy amounts in joules. Electronegativity is just a number. It doesn't have units. And we have calculated all of those things to get electronegativity for us and present them on this table here. Obviously, you don't need to memorize this. This is just a table that you want to reference. But what it does is it pairs together electron affinity, which increased as you went from left to right, and decreased as you went top to bottom. It also combines Z effective. Z effective increases as you go left to right. Generally speaking, as you go up top to bottom, it stays roughly the same. That's not necessarily true, but for our purposes in this class, it's close enough. And by putting those two things together, you get these numbers. Since the top right is the most electronegative, Fluorine is the most electronegative element on the periodic table. If you are paired with fluorine in an electron tug-of-war competition, you will lose, because fluorine is the highest electronegativity. It pulls electrons towards itself stronger than any other element. The big loser is francium. Francium's like, what the hell's an electron? Get this away from me. Now, as a general rule, left to right, electronegativity increases very strongly. There is one exception, and that's in the middle here. These 8 elements are called the noble metals, and the reason they're called the noble metals is because they tend to resist the effects of electron transfer. So, for example, if you have gold jewelry, you might notice that it doesn't tarnish or oxidize or anything like that. The reason for this is because gold's electronegativity is abnormally high, and it holds its electrons towards itself very strongly. Because of that, it won't react with oxygen, which is trying to take its electrons away. Oxygen's very good at doing this, but gold is very good at resisting it. So are platinum and all these other elements in here. Silver, not so much. Silver will tarnish, which is why you need to polish it if you use it as cutlery. But these noble metals have this specific property about them, which makes them useful for applications and makes them shiny and expensive and desirable, which is why they are noble. Other than that specific exception, the trends on this slide that you see are what we care about. So things will increase in electronegativity as you go up and to the right. Now, what do we use these numbers for? We're going to compare these numbers, so we'll have to go back to the slide to check the values of these atoms. We're going to compare 2 atoms that are bonded together. And by comparing the difference in their electronegativity, we can figure out if they are likely to form a covalent bond because they'll share electrons, an ionic bond because they'll transfer electrons because they're just too different, or if they're going to make something in between, like a polar covalent bond. All right. This page just summarizes up what I said about electron affinity, ionization energy, and electronegativity. So high electron affinity means atoms want electrons. Low ionization energy means it's easy to remove electrons. So those quantum mechanical effects you should be able to roughly correlate with position on the periodic table for electronegativity. Oops, I didn't mean to skip over that. Here's our blueprint that we are going to use to describe whether a bond is polar, nonpolar, or ionic. And there is one change that I really want to make, and I really don't like this right here. This right here shouldn't be 0.4, it should be 0.5. Which means that this down here should be 0.5. So go ahead and make that edit to your slide right now. This is actually an issue with your book. In organic chemistry, we consider this bond to be nonpolar. In fact, this is one of the most important nonpolar bonds there is. Now, there is some difference in electronegativity between these two. If we go back to the previous slide, and we look at carbon, carbon is 2.5, hydrogen's 2.1. We're going to calculate this, the difference or change in electronegativity, delta En. Delta En is always the bigger number minus the smaller number, so it'll always be a positive number. And the result that you get is going to go into this scale. Depending on the value that you get, you will assign the bond in question a term. So for CH, we would classify CH with its difference of 0.4 as pure covalent, because it is less than 0.5. And in other words, the difference between the two atoms has an electronegativity difference of roughly 0. Let's try that with a different atom and calculate its electronegativity. I keep saying electron affinity. Let's bond these two things together. So the first thing that we're going to do is we're going to go back to the previous slide. Got to find oxygen here. Oxygen is 3.5, carbon is 2.5, so we'll go back. We'll do the same thing. Bigger number minus smaller number. That's not even a number that was in there. What is wrong with me? There we go. I must have been going towards the sum or whatever. So this is my result. My electronegativity difference is 1. We're going to compare on the chart, and it's going to fall in here. And again, this is supposed to be 0.5. And so because I fell in this region, we would say the difference in electronegativity is intermediate, and that there is some shift of electrons towards the more electronegative atoms. So that means that the electrons would be more over here than they would over there. So if you are pure or polar covalent, what that means is that you are a covalent or molecular compound. Things that share electrons form covalent bonds. If the electronegativity difference is greater than 1.8, the electron gets transferred. 1.8 or so is the limit for which two atoms can share electrons. Beyond that, the electron is essentially taken. All right, there's our terms, and again, I am going to change these numbers here so that we're consistent with what you'll see in organic chemistry. So this is 0.5, and this is 0.5. For the upper end, 1.8 is pretty good. Some people use 2 as the upper end. It just depends on what textbook you're looking at. I like 1.8 because it puts more metals into the ionic bond category. But you could see that if the only thing that I need to get a covalent bond is to be between 0.5 and 1.8, that if you go back to the table here, there are some weird combinations that if I were to combine, say, this and this, I would get something that's nonpolar. And so I could make a covalent compound out of metals and nonmetals. And the reason that I'm bringing this up is because this is literally what I studied in graduate school. This is called organometallic chemistry, where you get metals doing covalent bonds and then they do interesting things. So if that is something that you find interest in later on after you've studied Chem 261, and then we talk about transition metals and stuff like that, that is a whole field of study that you can look into. I found it particularly interesting. And there's a lot more crazy chemistry out there beyond what we're studying here. So, to summarize what we're going to do today, to summarize what we're going to do tomorrow is we're going to take these numbers for our electronegativity results here, and we're going to display them graphically on a chart. And so we're going to do stuff like this, where we say, okay, this is the positive end, this is the negative end. We're going to do stuff like this, where we just illustrate it using symbology. And then what we're going to do is we're going to explore the effects of this property by drawing molecules and putting them next to each other and seeing what would happen. Because if I had a molecule that had this sort of dipole thing going on, and these two saw each other, you might think, oh, well, this is the opposite charge. They should attract. And the answer is, yeah, this is where intermolecular forces come from. Is these unequal distributions of electrons, either temporarily or permanently. So that's where we're going with all of this. And then finally, what we're going to do, and this is actually going to come up sooner, is we're going to learn how to name everything. In fact, I think tomorrow's lecture, let me just check where we are in the slides here. Tomorrow's lecture is going to just probably be name all the things. Yeah, because there's like 3 more slides in this. I guess we could finish this part today. Yeah, that's fine. Let's just finish the section here. And then we'll just name all the things tomorrow. So, again, let me write down my numbers here. Whenever you have 2 atoms that have some sort of bond together. Now, what type of bond this is would depend on their difference, and this is actually kind of disputed. HF is in the very weird gray area. It does split apart, which would make it ionic, but it does also stay bonded together somewhat, which makes it covalent. And that makes sense, given that its delta En is right on that cutoff. Since it falls on the cutoff, it's possible that it could just do both of those things. And we do observe it doing both of those things. But let's assume for now that it's covalent. And if it's covalent, what we could do is we could draw this symbol and this symbol. I didn't mean to actually draw over the symbols. I'm just bad with the stylus here. There we go. We use this delta symbol, and then we put a plus or a minus to indicate which side of the molecule is either gaining the electron density or losing it. The symbol delta represents partial. So these are partial charges. You could say this is like the molecule has a 0.5 charge on both sides of the electron, or maybe a 0.2 or 0.6 or whatever. But what it doesn't have is a whole charge. If it had whole charges, we would put actual symbols, plus and minus, on the appropriate sides. But that would indicate that it's ionic. If it's not ionic, we would just use these symbols instead. Okay. So again, we're only using delta symbols for covalent compounds. The other thing that we can use is this arrow, where this positive looking plus sign here is on the tail of the arrow, and then the pointer points at the negative side. So let's do a few examples, and I'm going to have you assign either nonpolar covalent, polar covalent, or ionic, and then give the correct symbology that you would use to describe its polarity. Now, we're going to assume that this little hyphen that I put in here is a bond. And we don't know what type of bond that is yet, so we need to go look up the electronegativity. So I need sodium, chlorine, bromine, iodine, nitrogen, and boron. And as it happens, I don't have any of these memorized. So let's go back to that chart. And we're going to do this because we have technology. I'm just going to type those all in. Oh, I should have known Cl. That one I know. What were the other ones? So we got boron is 2. Nitrogen is 3. That one I knew too. I'm just being stupid. I don't remember the rest of them. What were the other ones? Br and I. Uh-oh. I blindfolded everybody. I'm sorry. Br is 2.8. And I is 2.5. So there we go. So now it's in the chat. I can never forget it. You can't forget it because it's right there. I could just write the wrong number. That's what I could do, though. All right, so the first step that we're going to do is we're going to calculate delta En. 3 minus 0.9 is 2.1. And then we would go back to the previous chart that says, is it pure covalent, which is nonpolar covalent, polar covalent, or ionic? And this is above the threshold for ionic, which means that instead of drawing a covalent bond, what we would actually do is do that. Over here, delta electronegativity is the difference that is between these two. This is pure covalent. Again, nonpolar covalent is the same thing. I'm just using that because other textbooks use nonpolar covalent. Because it's nonpolar, essentially nonpolar, we don't have to write any symbols at all. But if you really wanted to, this would not be incorrect technically. It's just that these are so small that not writing them in this case would also be okay. Over here, though, the difference is striking, and we do want to write these. That should be an 8. I just miswrote. There we go. All right, so that's the correct symbology to be using for each of these. And again, if you have something that is pure covalent or nonpolar covalent, these are optional, and generally speaking, they're not written. Let me clear my text so that that's on the screen for you, so you can see it. All right, so I'm going to leave this slide for you to do some practice on. You can indicate the correct symbology to use for each of these molecules. Are the symbols supposed to be written as a superscript? So the charge is a superscript. The delta is just... I keep writing 8. The delta itself is just the Greek character D. Now, you could just put these as a symbol wherever you want to. So I'm going to leave that to you. Last slide that I want to go over today is just to say that even though we've been talking about these different molecules independently, so something might be covalent and something might be ionic, some circumstances do have both bonds present at once, just not in the same physical place. And so this would be something like a polyatomic ion. For instance, in ammonium chloride, we're going to talk about how to do Lewis structures later on, but you may have already seen this before. In ammonium, we have a positive charge overall. In chloride, we have a negative charge overall. This right here is an attraction between two ions. But this in the middle, holding the ammonium together, are covalent bonds. So some compounds, particularly ones that are polyatomic, will have covalent bonds holding together the polyatomic ion, and then an ionic bond holding together the two polyatomic ions, or the polyatomic ion and the anion, or whatever. So later on, we're going to be studying these bonds in more detail, but it's important to realize that these two bonds are not mutually exclusive from each other. Okay? My cat is telling me it's time to stop. Are you telling me it's time to stop? Meow. Do you want to say bye to everybody? I don't know if you can hear. Meow. Meow. Maya says we're done. So, I think we're done. I guess you heard her, so that's good. Alright, so when we come back tomorrow, we're going to name everything ever. So, I will see you for that. I'm going to go unlock quiz number 3. The deadline will be next week. Have a wonderful evening. Stay safe, stay healthy, stay home.